So we often hear about AI that can see, but how does that really work? It's not magic. It turns out you need a very specific, kind of brilliant type of architecture to make sense of all the complex data packed into an image. Today, we're diving deep into that solution, convolutional neural networks, or CNNs. Here's how we're going to break it down. First, we'll tackle why images are just such a tough nut to crack for regular networks. Then, we'll get into the elegant solutions, sharing the work and learning like we see. After that, we'll pop the hood and look at the convolution itself before seeing these networks out in the real world doing amazing things. All right, so first things first. To really get why CNNs are such a big deal, you have to understand the problem they were built to solve. Why can't we just throw a standard neural network at an image and call it a day? Okay, if you've ever dealt with data in a database, you know it's nice and tidy, right? You've got neat columns, age, price, maybe mileage. A standard, fully connected network can handle that, no problem. But an image isn't a simple row. A single, pretty small color image has over 150,000 values to deal with. The moment you feed that into a standard network, you have an explosion of complexity. And just look at the numbers here. It's staggering. For a really basic visual task, a traditional network would need to learn over 150,000 different parameters. But a convolutional network, it can approach the same problem with just about 2,000. That's, what, a 98% drop in complexity? It just goes to show how wildly inefficient the old way really is. And here's the kicker. It's not just about being bloated. That giant network with all its parameters is actually worse at the job. It gets really good at memorizing the training images, sure, but show it a new picture, it totally fails to generalize. The smaller, specialized CNN isn't just more efficient, it's actually much better at learning the patterns that really matter. So this leads us to the first really brilliant idea inside a CNN. If learning a unique weight for every single pixel location is a total disaster, how do you get around that? Well, the answer is pretty elegant. You share the workload. This core idea is called parameter sharing. So instead of trying to learn a cat ear detector for the top left of an image and then a totally separate one for the bottom right, a CNN just learns one cat ear detector. It then slides this single filter, which we call a kernel, across the whole image. It's a learn once, apply everywhere kind of strategy. And when you think about it, this is just common sense. A cat's ear looks like a cat's ear, whether it's on the left side of the photo or the right. Forcing a network to relearn that same exact feature for every single spot on the grid isn't just inefficient, it's just illogical. Okay, so parameter sharing makes CNNs super efficient, but there's another, deeper reason they work so well. Their whole structure is basically inspired by a fundamental property of how we actually see and process the world. Let's break down these two key ideas: equivariance and invariance. Imagine you have an app that draws a nice little box around every person in a photo. If someone in the photo moves to the right, you expect the box to move right there with them. That's equivariance. The output moves with the input. Now imagine a different app that just tells you, yep, there's a person in this photo. If that person moves around, the label, that final answer, should not change. That's invariance. And because CNNs slide that same filter everywhere, they are naturally built to be translation equivariant. This is not a lucky accident, it's a core design choice. It's what we call a powerful inductive bias. It's like a built-in assumption that makes the network incredibly good at handling visual data, because it forces it to learn things that don't depend on where an object is. Okay, so we've covered the why CNNs are so effective. Now let's get our hands a little dirty and look at the how. What is actually happening inside that core building block, the convolutional layer? You know, the operation itself is surprisingly simple. It's a three-step dance. 1, you take a small filter, the kernel, and lay it over a patch of the image. 2, you do some simple math, a weighted sum of the pixels in that patch. And 3, you slide the kernel over a bit and repeat. That's it. You just do that over and over across the entire image, creating a new feature map that lights up wherever that specific feature was found. So a few terms you'll hear. First is kernel size. This is just the size of that sliding window. A small 3x3 kernel is great at spotting fine-grained details, while a bigger 7x7 kernel is looking at broader patterns. Next up is stride. This is simply how far the kernel jumps each time it moves. A stride of 1 is meticulous, examining every single position. A larger stride, on the other hand, skips ahead, which shrinks the output and helps the network focus on the bigger picture. And finally, there's dilation. This is a really clever trick. It's like spreading out the points of your kernel, letting it see a wider area and gather more context, all without actually adding any new parameters or computational cost. It's a free lunch. So, we've got these super efficient, vision-inspired building blocks. What can we actually build with them? Let's take a look at some of the incredible, real-world tasks that CNNs are powering every day. We're going to touch on 3 of the most fundamental jobs in computer vision. Each one gets progressively more complex. We've got classification, then detection, and finally, segmentation. First up, the most basic task, image classification. The network answers one simple question. What's the main thing in this picture? It takes the whole image as input and spits out a single label, like dog or bicycle. Next, we level up to object detection. This is more advanced. It's not just asking what, it's also asking where. The output here isn't just a label, it's a set of bounding boxes drawn around each object, telling you exactly where they are. And finally, we have semantic segmentation. This is the most detailed task of all. Here, the network has to classify every single pixel in the image. The question becomes, what category does this tiny dot belong to? The output is a complete, pixel-perfect map of the entire scene. This is road, this is sky, this is a tree. So to wrap it all up, it really comes down to those 2 powerful ideas. 1, sharing parameters to be incredibly efficient, and 2, building in translation equivariance to act more like our own visual system. Those 2 principles are what allow CNNs to learn such powerful features from images. And those features are the foundation for everything from simple classification to a complete pixel-level understanding of a scene. You know, the very first CNNs were directly inspired by how the visual cortex in animals is wired. It really makes you wonder, what other systems in nature could be the blueprint for the next big AI breakthrough? I mean, think about the way a swarm of bees communicates, or how an ant colony organizes itself, or even how DNA stores information. The answers might be all around us. Hey, if you enjoyed this deep dive, do me a favor and share this explainer with someone else who might find it interesting. And of course, be sure to subscribe for more. Thanks for tuning in.